uses to run Xserver. Xserver is like the background process that runs like the GUI environment. I do have access to a bash prompt, but I can't display a PDF without having Xserver on there, without getting very fancy. And I don't know, I'm going to try switching to a earlier kernel version, I guess. We'll see if that helps. Anyway, so I am forced, unfortunately, in this course, which in theory is about Linux, to present Linux material on the hated Windows operating system, which is just like a real kick in the teeth, you know. It's like, man, I wish that things had turned out differently, but here we are. Anyway, so got a lot of material to get through, so we need to make our best attempt. Okay, I want to make a deal with you guys. All right. I will extend the deadline on assignment 2 to Wednesday, on the condition that MSAFs and extensions still only can get you through to Thursday, because we have to have the assignment due before we write the exam. That's a rule.
Isn't it already due Wednesday?
Is it not? Is it already?
Third.
Yeah, third.
Well, who modified that? All right, well, never mind then.
It's so funny, that just happened in my calculus class yesterday, the exact same thing.
Everything fine.
Actually, this is an absolute win.
I thought you were going to extend it further.
Yeah, me too. I want to say
I
Friday.
was
Yeah,
under
Friday
the
would be
impression
nice.
that that's, well, I mean, we can't have it Friday. We're writing the exam at 9 a.m. on
I
Fridays.
mean, I want to try to finish it before Wednesday anyway, because I have work to do.
Wow.
I mean, in my JC3
Emphasis on
class,
try.
in my JC3 class, we had an exam that was on like a Friday, and like we saw an assignment due the following Sunday.
Well, that's not, that's against the rules, but, you know, all right, fine. If one JC3 wants to do it, they're welcome to it, but no, the assignment, all of the material needs to be finished before the exam happens. It depends on whether you consider assignments to be for the purpose of learning and learning to be for the purpose of writing the exam or not, you know. But anyway, so we have a little bit to cover here, which we will get through. So, just quickly reviewing. So we were talking about regular expressions, or regexes. The regular expression is a mechanism for attempting to match texts, create a pattern which matches several different types of text. You can produce regular expressions that match, for example, street addresses. You can create a regular expression that matches email addresses. You can then take the results that are given to you by the regular expression and modify them, collect them, do whatever you want with them in whichever way you wish. They're a bit like blob patterns, but not really. So, in terms of syntax, we have alternation, right? We can say this regular expression will match either A or B, where A and B can be any other regular expression recursively, or we can group alternatives so that, in the middle of a word we can have one alternative or another. This particular regular expression would match either tomato or tomato. This is generally true of regular expressions. Like other operators as well, round braces which you put in there cluster the characters together and give them associativity. Notice also that this would not be interpreted A, Y, or A, and then H. These things are associative as far as the next, they're associated as far as the next operator symbol inside of the regular expression itself. Are we recording, by the way?
Yes.
Wonderful, thank you. Good. In addition, we have the plus symbol, which indicates one or more occurrences of the specific character that comes before it, in contrast to the alternation. So, for example, A plus B plus C matches A, B, C, A, B, B, C, etc., etc. The plus means that you must have at least one of these characters occur. The multiplication symbol, or the asterisk, indicates that you may have 0 or more times that character occurring. So if we examine the following regular expression, we have na with a comma and a space, plus, and then we have 3 alternative endings, Katamari Damacy, Batman, and Hey Hey Goodbye. All 3 of these patterns are matched. Notice that it doesn't matter how many of these single instances of na occur, we still get matches on all of them. Does that make sense? If we had a star here, right there, instead of a plus sign, then we could have na Batman, immediately with none of the lowercase na's occurring. Does that make sense? Any questions so far? Good. Postfix asterisk specifies 0 or more occurrences, as I have said. So x, y star z matches x, z, including all of the matches that would have been previously matched by the plus symbol. So, ba, na, with the star symbol, will match ba, banana, not the second part if you put a space in it. All of this doesn't match the end here. Anyway, does not match ham sandwich. Make sense? So regular expressions are the kind of thing where the individual pieces are not that complicated, but the manner of their composition can produce complexity in them. So when you guys do the lab this afternoon, you'll see more complicated regular expressions than these. You'll be required to compose some. But just remember, just like any other type of programming, everything can be decomposed into these fundamental operators, and plus a couple of different selector type things. But so the wildcard character period. When a period occurs inside of a regular expression, that is the same function essentially as the single character wildcard from blob patterns, that is the question mark. So basically, if you include the period, in this regular expression, we're matching any time an m is followed by a space and then some other character occurs. So instances like here and here and here. And we are also matching any time two E's occur with exactly two characters between them. Here, 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 etc. Does that make sense? Good. So, you may be saying to yourself, okay, sure, but certainly at some point there must be some Unix command which you are about to teach us, which actually uses these things, which I have at some length discussed. Well, the command is called Grep. Don't ask me why it's called that, but it's fun to make puns with. So while find searches the names of files, Grep searches the contents of files. So if you have a gigantic series of directories, perhaps containing the very lecture slides that this course, all of the LaTeX files for all of the slides that are used in this course, if you're trying to find a particular file name, find is what you want to use. But if you're trying to find all of the occurrences, say, of, the word if statement, or this series of words, if statement, if you're looking for all occurrences of that inside of a directory, then grep is the command that you want. As with many commands, we can specify multiple files to be searched using blob patterns, and we can search directories recursively using the R flag. You'll want to use the R flag most of the time with this one. If no file is specified, grep searches your working directory. If you also use the R flag, it searches your working directory and all subdirectories, which is, again, what you want to be doing most of the time. The E flag allows the use of extended regular expressions, which have some additional operators versus the sort of regular loadout. And I wish I could demonstrate this, but well, hello. I see you've decided to join us. See, I was kind of hoping that would be the case, because I saw briefly that no, I think it's still glitching out. Give it some time to figure itself out. Yes. So you'll see a number of examples of when you would want to use this when we get into the lab. But regular expressions can also be used to perform modifications of files that you read in using the standard Linux procedures. There is another program called SED, S-E-D, which stands for Stream Editor, which allows you to not only specify regular expressions, but also perform replacements in files according to the regular expressions that you've written. So it's like a find and replace operation over your entire operating system, rather than just individual files, which of course can be very useful. But let's talk about our extended set of regular expressions, shall we? So, in grep, the vertical bar character indicating alternation works as you would expect. The braces also work as you would expect. So it was the best, worst of times would match either it was the best of times or it was the worst of times, which is a literary reference. Ah! You can use square braces to alternate many characters. So rather than, doing A or B or C or D or E, etc. If you use square braces, it will simply alternate all of the characters that occur inside of the square braces. So this will match any lowercase letter, any single lowercase letter. We might also note that our regular expressions are delimited by single quote characters. Can anybody tell me why we are using single quote characters to denote regular expressions here? Any guesses? Something to do with characters is a good guess. So you guys remember the glob patterns? Yeah? You guys remember how anything inside of single quotes does not get expanded?
Yeah.
Yeah. So with glob patterns, basically, since regular expressions and glob patterns are using the same characters for a lot of their different operations, think, for example, the star character being used in glob pattern, meaning, many or one anything character, right? Multiple wildcards. In regular expressions, that has a different meaning. It means 0 or more repetitions of whatever went before. So these things conflict. Because of the way that the terminal works, all glob patterns are expanded prior to the command being executed, unless those glob patterns occur inside of single quote environments. So by putting our regular expressions inside of single quotes, we are freeing up, essentially, the specific characters that are used by the regular expressions from interference by glob. Glob will not touch it because we have put it in single quotes. Does that make sense? Sort of? A little bit? Good. Period is still the single character wildcard in the extended Grep regular expressions. So super dot REO will match super A REO, super B REO, super C REO, etc. Question?
Would that also match if there wasn't, like, would the period also match with the space? Like if you just had
Yes.
space REO, like
Yeah. It's a wildcard character, so it could be literally any character, including the weird ones that don't print, like tab, that might not necessarily print, like tab and new line. Although we have specific things that in regular expressions we indicate new line characters using specific other characters. But yes. The question mark is a postfix operator indicating an item is optional. Do you guys know what a postfix operator is?
No.
No?
Go at the end.
Yes, it's an operator that goes at the end instead of the beginning. So if you think the negative sign as applied to an integer is a prefix operator performing negation, basically a postfix operator would be, you would have the number and then the sign. And in this case, we have the character and then the symbol. This is not terribly complicated. This is the way that all of the star and plus operators work as well. So A question mark B question mark C matches exclusively, actually, C, AC, BC, and ABC. These are, you can either include them or not. Which, you might be asking yourself, how previously would we have done this? How would we have indicated the presence? Like alternation with nothing? No characters in an alternative? So, The star postfix operator works as it did before. The plus postfix operator also works as it did before. As shown in the above example, round braces are still used for grouping. Well, praise be. I think this might work now, but we'll see. Needs a minute still to warm up. My computer seems to have somewhat recovered, so we're going to do some examples on the computer of these guys as soon as it, recovers itself. So, although we have square braces to alternate larger groups of single characters, some common groups of characters have been collected up for us. So you can indicate any of these character groups using these tags, which you just kind of insert into the regular expression. So you have alnum for alphanumerics, that is to say both alphabetics and numerics. Alpha is alphabetics, digit is numerics, space is all types of white space, space, vertical tab, horizontal tab, and new line. Blank is just spaces and tabs, so not including things like new line. Lower is lowercase alphabetics, and upper is uppercase alphabetics. So, this somewhat complicated regular expression matches all things written in camel case. Camel case is where you basically take out all of the spaces, and then anytime a new word occurs, you capitalize that letter. It's a naming convention which is used pretty extensively inside the Haskell programming language. But yeah, so we've got a lower and then a series of uppercase characters followed by one uppercase and at least one lowercase, and you have at least 0 of those, followed by a blank, and that is camel case. Make sense? Hopefully. So, how are we doing, Mr. Computer? So nice of you to join us. There we go. Back to the future. So, let's do a couple of examples then. So I'll show you the easy way first. An easy way if you just want to search through files without using any regular expressions. Grep, RA, and then the search phrase, which in this case, let's say structure. Man, my computer is slow at the moment. But you can see, well, you can mostly see anyway, it tells me not only the file in which the match occurred, it also gives me the line in that file where the match occurred as well. Low disk space. Well, that's interesting. But it says it has 0 bytes. What? I don't know what's going on. I have to fix my computer. Anyway, so. Good. There we go. So let's try some alternation. Let's say we want to match with extended regular expressions either the word your or you are. Yeah. Oh, right, can't do that. Gotta escape that. Okay, no? Okay, we'll just do something else then. So, you can see we're matching alternatives, either you or your. That really doesn't show up very well. I'm going to fill the lights a little bit more, I think. Better?
Yeah.
Yeah. Maybe leave one on. There. Good. So, there we go. If we want to match something with, which includes the square brace notation, let's say WRST with any vowel. So worst, 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 or worst. Any of those different words. As you can see, only one of those is valid English, so only one of, well, I guess bratwurst is a type of worst, but you can see that it only matches that. We can also use the period. To match anything, any place that we get an F, a character, and then an R, using the regular expression that I just showed you. And apparently we have matches inside of binary files as well, which are probably essentially random. Yes?
When I try to do this on my Mac, I keep getting Grep warning, recursive search of standard input. What does that mean?
Recursive search of standard input.
Well, it says STDIN.
So it's recursively searching standard input. Oh,
Is it because I'm on a Mac?
Try putting a period afterwards. Did that work? It might be defaulting to also searching standard input.
It worked.
It worked? Yeah, it might be defaulting to also searching standard input because no, the way I was doing it, no folder was being specified.
Okay, so I need to specify a filter.
Yeah, so if you specify the current working directory with a single period character, it seems that resolves that issue.
Thank you.
You're welcome. Any other questions? I'm glad that you're following along and doing the commands, because that is an effective way to learn. So, alternation. So we can say something like they, but with a question mark after the Y, matches all instances of the, and doesn't seem that I used the word they anywhere in there, so it goes. Let's try something else. So it doesn't really show up, I guess, but anywhere any word THE occurs with a space immediately afterwards, the space is also being matched, although there's nothing to highlight because it's a space. Which means perhaps I should refine my search somewhat, eh? Yeah. There, that'll do. So, my search this time easier to just do that. The space question mark S matches all points where the word the has a space and then the next word starts with an S. And it also matches instances of the word these, or at least the first 4 characters of it, because, of course, the space has been made optional. Does that make sense? Any questions? Good. So, I kind of want to just grab this. Oh, man, that is pretty terrible. Let's say we match all instances of one uppercase letter followed by at least one lowercase letter. You don't say. Followed by a blank. So this will match any word which is in uppercase in any file in the search directories. Cool? Good. So we have a few more. We can pipe grep commands together to find the union of the 2 grep commands. So if you want to, pick out one piece of text and then pick out other pieces of text in the lines that piece of text returned, you can feed the standard output of grep into grep as standard input. Of course, this will, I think, require you to leave the period out in that case. Also notice that the recursive flag is not being used on this one, which might be the problem that you were having. If we have the caret character inside of square braces, this will match anything but the indicated regular expression. So this will match anything but ordinary, which is another joke. Caret at the beginning of a pattern requires the pattern to start at the beginning of the line. So if you put the caret character here, then this requires the line to start. Basically, it requires the match to start at the beginning of the line. The $sign has a similar effect with the with the end. So the $sign requires the match to happen at the end of the line. So if you put both the caret and the $sign in, you're doing essentially whole line matching. So all of your matches will be either entire lines of files or no lines at all. Make sense? So, now let's talk about sed. Any good programmer knows that find and replace is the most valuable tool any text editor can have. If you've not discovered this yet, you will. Sed, or stream editor, lets us perform find and replace operations with all of the power of dash and regular expressions over your entire operating system, if you so choose. The regular expression sed tells you where to perform substitutions. The string is the replacement text. So sed in I mode, sed has a very large number of modes and configurations. So if you're interested in reading the man pages on it, I encourage you to do so. But in general, for a find and replace operation, you use S and G options inside of the pattern, right? The regular expression is placed between the first forward slash and the second, and then the string you wish to replace it with is between the second and the third. So essentially, all patterns which match the regular expression will be substituted for the replacement text. The following operation, for example, where we have oak or spruce or larch or ash or maple being replaced with tree, replaces any of the above specified types of trees with the string tree where they occur. However, because we have not bothered to put any spaces in our regular expression, a word like cloak will turn into clotree, which is kind of funny. Or bash will be a tree, which is also kind of funny. So I want to give you a dire warning with respect to the use of the stream editor and your precious files. This thing can overwrite large quantities of data very, very quickly in one step with no possible way to recover that data. So, for example, if you put dot star, right, so as multiple wildcard characters, and then put anything here, basically everything in every file will be replaced on every line with whatever you've put here. So that would be what I would consider a dangerous operation. I highly recommend, before performing any sed operations, backing up whatever you're going to be operating over. Because you can, it's another one of those Linux situations where one character misplaced can completely destroy your entire operating system. Or at least, you can't destroy your operating system without invoking superuser, but you can certainly destroy, all of your family photos, for instance, or anything that you value. It's another instance of read the manual. So, of course, we can combine this with the power of find to be able to perform very crazy operations, such as performing find and replace operations over every file in the file system that we have permissions for, find and replace over all files in a directory and subdirectories of a particular file type, perform find and replace on a file that we don't know the exact location of, etc., etc., etc. Right? Basically, anything you use find to do you can pipe the results of find into other commands and then perform operations over those found files. You know, it might not be anything so insidious as, you know, performing performing this type of a find and replace. You might just be, you know, copying it to a temporary folder as given in the previous example. But in general, that's a useful thing to know how to do. Any questions? Okay. So, I just have one last thing to talk about, and then we'll be on to our C topic for today. Just give it a little more light in here. So, in practice, searching commands can take a long time to execute, since they are sifting through, in some cases, gigabytes worth of data. For example, if you were to search, you know, your entire home directory for something, right? What you can do is you can use find to narrow down the search to only those text files which you know you're trying to search in. So, for example, if you know that you're wanting to look inside of LaTeX source files, you can find all LaTeX source files first using find, pipe that to Grep, and that will significantly reduce the amount of time that it takes to perform that search. Not to mention, you will likely get far fewer erroneous results. So, if we have to perform a Grep search with a large search area, but we know something about the files we need to search, like their file extension, for example, we can pipe the results of find into Grep to substantially increase the speed of the search. One problem we'll run into, however, is that xargs considers both new lines and space characters to be argument separators. This can be a real problem if our directories contain spaces. So, and I was talking about this last time in class, find will include any spaces which might be contained inside of the directory structure or file names which you're using on your computer, right? Xargs thinks that that's an argument separator, right? So we have to tell our xargs that it's not an argument separator. We have to tell xargs that new lines only are argument separators. So, this is what you do. You apply print 0 to find. You apply the O tag to xargs, not to Grep, to xargs, and that works. So, for example, if I were to take a look, find all star.txt files, sure. There they all are. Print 0. You'll notice that by looking at the results of print 0, we basically have run together all of these files, right? The separators no longer appear. What it's done is it's taken new line, right, and it's replaced it with a new character, I believe the null character. So, obviously it won't show up. Using the 0 argument on xargs tells xargs to only use this character being inserted by find as the separator. So, xargs 0, for example, cat. And you can see that cat has catted or printed the contents of all files indicated. We can use less, you know, we can use touch, anything? I don't know. All right. Good. So much for that. Any questions? Okay, good. Right, moving right along. Good. So we're going to talk about data structures. The course is nearly finished. We only have some miscellaneous points to also talk about with C programming, but with the conclusion of our previous topic, we have in fact concluded all of the Linux and Unix related material in this class. Praise be. As I'm sure you're all thinking, thank goodness he hasn't given us any more. You have taken perhaps your first tender steps in the direction of true Linux mastery. You are not Linux experts at this point in time for having done this course. That requires years and years of dealing with exactly the type of problem that I had this morning that prevented me from showing my slides, at least for a little bit. So, yeah. I hope that you have found Unix-like environments to be sufficiently interesting and profitable to warrant your continued study and use of the environment. Windows is terrible. Any alternative is better. So let's talk some more about C programming. We're going to talk about data structures. We'll get into a little bit of material that's of a more data structures and algorithms flavor, which, you know, how many of you are taking, is it 1DM3 does a little bit of this stuff, right? No, not really? You've talked about graph theory, I hope, though, right? Yeah.
Not yet. I think it's like next one.
The next topic is graph. Ah! I'm going to beat him. Well, maybe. We'll see.
It's not hard.
Yeah. So, anyway. So as opposed to that magical land of pure mathematics where everything always works out nicely, here we have to actually program with these highly abstract concepts. So, yes?
If the slide's supposed to say software and 2MP3.
No, don't worry about it. The C side of this was taken from that course because it's also a C programming course. Yeah, which I also taught and developed all the slides for. So, yeah. But thank you for noticing. Maybe I'll just fix that if I have enough memory left on the computer, because it seems to think I'm out of memory. Compile.
Guys.
Yeah. is gonna prevent me from. Yeah. It does genuinely think that I have 0 hard disk space left, which is fascinating. Okay, well, that hopefully won't interfere with the writing of C programs. I think it's going to interfere with the writing of C programs. Like, can I delete something? Why is my file system full? Doesn't make any sense. Can I delete this? And it still thinks it's trash, empty trash. Here we go. Still thinks it's 0 bytes. Okay, well, all right. Anyway, so let's talk about structures. Roughly speaking, how many of you guys have used Haskell before? So think tuples. Think tuples in Haskell. Up to this point, we have had no abstract, well, records. If you've used records in Haskell, they're more like records, but anyway. Up to this point, we have had no abstraction mechanisms in C besides functions. Unless you count pointers, which personally I don't. Consider the following scenario. Let's imagine we have a database that contains the names, email addresses, and pinball high scores of customers stored as a CSV file. Pardon me, as a CSV file. So, we've got John Boring, Sally Plain, Nancy Snore, and Peter Bland, and Thamarius the High Elf. We could group this data by field into arrays, or we could make a struct to record the data type. So, what a struct is it's a means of grouping several variables together to form one supervariable. A structure groups several variables together into a single data type. Structures are roughly analogous to classes in Python if you remove methods. So, you all know classes in Python, right? Yeah. So the thing that distinguishes a class in any object-oriented programming language, not just Python, is the combination of data storage in the form of member variables to a class with member functions. And I'm using C++ nomenclature here because this is a C course and it seems more appropriate than using Python syntax. So essentially, when you have a class, you have a group of data and you have operations that are meant to operate on that data, right? In C, you've got half of that. You have the ability to group data, and any operations which you want to perform over that data cannot get grouped with the data because there's no concept of that in C. You just write functions and use the functions and import the functions and do anything you want with the functions, but there's no way of setting up things like inheritance and polymorphism and that sort of fancy abstract stuff that object-oriented is so good at. So, speaking about our previous example of these data from a CSV file, we would have a string name, a string email, and an integer representing the pinball high score. All of these things would be collected into a structure called customer. This, we may now use struct customer to indicate the creation of such a record which must have all of these fields, right? So, whether or not you use them, the fields are always created when you create a new structure. So, from a programming perspective in C, what you're doing is you're creating a variable of the structure type, right? So, this creates a new data type customer with fields name, email, and pinball. So, The fields of a structure are accessed through dot syntax. So if, for example, I create an array of these customer structures, right, I may access the elements of the array through regular array indexing notation, but the fields are accessed using dot notation in the same manner as Python, in the same manner as lots of languages. So if I wanted to create the first entry in our array of structures, we just simply assign strings to our uninitialized character arrays in the same way that you would normally do to populate those with data. You would initialize, basically this is just, the process. Yes?
So, like on the first line, you're assigning John Boring to index 0 in the array. Is that what it's doing?
Index 0 dot name. So let me visualize it for you. So in a normal, plain, boring array, right, you have these individual elements, right? 0, 1, 2, 3, 4, 5, 6. Everything's fine. In an excellent, amazing structure array, what you get is you get larger buckets where you have name, email, and pinball, which all have, things that they do, right? Incidentally, name it will be a pointer to a string that's held elsewhere, right? So it's like John is over here, and this is a pointer there. Email is, John at John.John, right? And then this would just be a number, so it's just held locally because it's not a pointer.
So like for the next person, you would be doing it at one.name, one.email.
Yes.
Okay.
Yeah, exactly. Question?
So it's basically just like a 2D array, but rather than index numbers, you have names for those other rows.
Yeah, that's a good way of thinking about it, yes. Yeah, it's very much like a 2D array, but with labels for the various variable names. Also, unlike a two-dimensional array, these can have whatever data type you like. So basically what's going on in memory is that structures are stored very much like an array would be, right? So let's say we had a structure that contained 2 chars, an int, and a long int, right? So in terms of the number of bytes, we have 1 byte, 1 byte, 4 bytes, 8 bytes, right? So how that gets stored in memory, you have 1 byte, 1 byte, 4 bytes, 8 bytes, right? X, Y, Z, and A. So that's X, Y, Z, and A, right? So in the same way that an array is doing everything by starting with an initial pointer to the first element of the data structure, and then doing everything by calculating an offset, right? Structures are actually working in via the exact same mechanism. The structure itself, my boy's 0 in this case, is a pointer to the first element in the structure, right? And then the subsequent elements in the structure are calculated for you by C as offsets from that original pointer. Does that make sense? So it's the same way that arrays are working if you sort of peel back the layer where we're not supposed to look beyond because here lie monsters. You know, if you peel back the hood and take a look at what's going on underneath, it's really like not hugely different from how an array works. And like, frankly, you could reconstruct this functionality using pointers and arithmetic if you really, really, really wanted to. If you were, you know, so long as you were consistent with it, right? It's kind of interesting, like all of the advanced constructs in C, they all boil down to pointer operations. Like, basically, using structures is a way to almost half forget that you're using pointers to do everything. Even things like function calls are all pointer operations, where a function itself is a pointer to a place in memory where instructions are stored rather than data, right? So basically, what calling a function means is it means you load a particular memory address where instructions are being stored, and then you carry on with those instructions, once you've created the stack frame and put the data in the correct place and all of that sort of thing. There's more to it than just that, but that's the main operation, is you're jumping to some other portion of the code indicated by a pointer, just like everything else. That's why understanding pointers is so critically fundamental to understanding C as a language, right? Question?
So what about other programming languages? Do they also reference pointers?
Do they compile to C? A lot of languages actually do.
Python?
So here's a question. Do you know what language the Python interpreter is written in?
C.
It's written in C. So everything that's in Python, fundamentally it's all pointer operations. Yeah. Basically, it's like, I want to say something like, that's computing, Basically, all you have in computing are these fundamental operations which we've talked about in C programming. You can write direct values, or you can write references to other cells of memory. And read, write those, and everything else is just organization that's been layered on top of that, so that you don't have to worry about it. And the reason for this is because fundamentally these all boil down to the basic and essential operations performed by the CPU itself, right? Things like addition, subtraction, whatever, right? The CPU will perform at least twice the number of load and store operations that it does direct arithmetic expressions. So by volume, 66% of what a CPU does for any given operation is pointer manipulation. So yeah, pointers are important. Any other questions? These are good questions. Okay, so this is one way of going about it. You can also initialize a structure with the following notation, which should somewhat strongly resemble the way that you would initialize an array. I wonder if there's some kind of correspondence between the way that arrays and structures are handled under the hood. But if you include each of the values which you want to write into the structure in the form of a comma-delimited curly brace, comma-separated curly brace delimited phrase, then it will simply slot things into the correct place, assuming you've put things in the correct order. This is position dependent, right? The first one will be the first structure, field, the second one will be the second structure field, etc. Right? Good. This last line, the purpose is to demonstrate that both read and write accesses use the same dot notation in both cases. So let's talk about some quality of life improvements. Ordinarily, in order to use a structure, you have to actually include the struct keyword before the name of the structure data type every time it's used in the program, unless you type def it out, right? So it's kind of like long int, right? If you are using a long int anywhere you use, like, you know, in function arguments or return types or anything, you just have to type long every time, right? Which is annoying, which is what type defs are basically for, is to make the writing of data type names less annoying. So this is kind of a convention rather than a strict requirement, but struct customer and then capitalize the same name, that's normally how structures are done. So now, after this line of code, all uses of struct customer could be replaced with just customer capitalization, which is, you know, faster to type. It's a quality of life improvement. We can also define a default structure variable as follows. So on the last line of the structure before the terminating semicolon, incidentally, I just like to point out that these things do require a semicolon. That is a requirement syntactically. If you want, you can set default values for all of the fields of a structure, cust def. Basically what this is doing is it's creating a global variable which you can initialize your structures with later on. So for example, if we wanted to initialize our entire you know, array of customers with this you know, default value, rather than just have the whole thing be filled with junk data, which is, of course, the default for everything in C. Custom def, custom def, custom def, custom def, custom def. This basically gets replaced with this guy, right? Just gets immediately substituted in. Does that make sense? Question?
If it's not inside the, I guess, the curly braces, how is it accessing the memory for the structure?
If what is not inside the curly braces?
The cust.def.
Oh, this is not a field. So let me do it on the board then. So basically, you're saying, okay, so customers is a new data type that contains name, email, and pinball, right? What this line at the bottom does is it assigns a new variable, def cust, which says essentially name becomes none, email becomes none, and pinball becomes 0, right? It's a separate entity, right? So if you create a variable later on, let's say, you know, customer X is equal to def cust. Brings this definition in here, X gets initialized with all of those values, but it becomes its own separate record so that it tracks data separately.
But how does it connect? Like, how do they relate if there isn't any, I guess, referencing from structure customer to the other one?
So,
Use any names or
right, because it's like, we're not using any of these names here. That's your question?
or depth, that doesn't have any relation either, right?
Doesn't have any relation to what?
To the structure customer, it doesn't have any of these name elements.
It does the same thing that we would, like, okay, one second. So you see how we're initializing structure customer is Mavoy here instead of, it's a separate one. You see how we're doing this here? And it's relying on the position of each of these values to indicate which field of the structure it gets written to.
So it's based on the position of data in the other structure?
Yes, precisely.
What if you have two structures that have the same, I guess, position of data? If you made something else that is a named customer, like a structure.
So if you, let's say you have customers too, which had first name, last name, and Space Invaders score, so that the data types would be exactly the same, but the structure would be a different name. You could use the same thing to initialize both.
Okay.
Technically speaking, you could use the same thing to initialize both. However, I would recommend writing specific ones for specific structures. Right?
All right, I got it.
Yeah. That's one of the funny things about C. It's sometimes we're up against the language itself, sometimes we're up against convention. Yes?
Two quick questions. First, kind of like a branch off what he was asking. So in this example here, because the semicolon doesn't come until after we've defined cusdef, cusdef knows it is the structured customer because it's like we're basically defining the elements of customer while we're assigning it as the data type of cusdef. Correct?
Yeah, it'll pick up the fact that it's being included in this guy. Yeah.
Okay.
Although, at what I said previously, this could still be used to initialize anything with the same type signature, because C is ultimately very loose. You can initialize integers with characters if you want to and stuff like that. But
Okay.
question number 2.
Number 2. So if we're basically just dealing with arrays under the hood, if we were to define cusdef and then later come and assign, Jimmy Bob, Jimmy at yahoo.ca, and then some number, would we have to malloc memory to account for the larger strings that we have reversing defined?
Yes. Well, you have 2 options, right? One would be to realloc the pointer, like this guy, the thing that's pointing to the string. The other would be to just assign it to a new, create a new string, assign a pointer to that string to this, right? And then just assume that the computer deals with the memory that you just leaked, right? Incidentally, that's what a memory leak is when you lose track of data by assuming it just sort of dissolves into the ether when you're finished with it. Some languages have subroutines called garbage collection, which goes and rounds up data to which nothing still points. But, 3 guesses as to whether C does that. It doesn't. So, any other questions about this? These are excellent questions. So, some additional notes. Structure members may be variables of primitive data types or aggregate data types such as arrays or other structures. The main point, I'll get to the main point. A structure may not, however, contain an instance of itself. It may, however, contain a pointer to an instance of itself. So that's an important distinction, right? Many advanced data structures, such as trees, rely on this idea that you can have basically a node in a tree described as a structure, and then you can point to other nodes in a tree from the one node in the tree that you're in. We do refer to these as recursive or self-referential data structures, despite the fact that on a technical from a technical view, the structure itself is not allowed to contain itself recursively. It must point to other instances of itself. So there's a very good reason for this. And basically it comes down to the size of function. Basically, any structure which size of cannot compute is not a valid structure in C, right? So another way of saying this, let's say you wanted to allocate a data structure using malloc, right? How much memory does it get? If it contains infinite instances of itself, how much memory do you assign it, right? Well, the answer is you can't decide how much memory you get to assign it, right? Like, if you have a structure that contains the same structure, that contains the same structure, that contains the same structure, although these are getting smaller as braces, if you imagine them as having like the same amount of memory, like, it goes off to infinity. There's no way to actually determine how big the structure is because it's like, well, it's infinite, right? So the way that you break that is you say, okay, I have a structure and I will contain references to other structures. The references themselves are of fixed size, right? So by making these into pointers, we absolutely and with precision know how big the structure itself is, which is necessary if you're going to perform any memory operations on it, right? So, and this is kind of jumping ahead of the slides a little bit, any data structure that pretends to be infinite, like certain data structures in Python that shall remain nameless, looking at you lists, basically they're not storing things sequentially in memory like C does. They are storing them in the form of what we're going to study later, linked lists, where each node in basically each element in a list is a node in this type of structure where the next item in the list is pointed to by the previous. That way, you can have data structures that behave like they're infinite when in fact they are not, right? Does that make sense? Good. So, you may declare any number of variables after a structure definition, not just the default one shown on the previous slide. So if you want to provide multiple different ways of initializing a structure, that's perfectly possible. You may even omit the structure tag, in our case customer, and declare all of your variables in the global namespace. If you want, you don't have to group it with the structure, but then you would have to include data type information, just like you would any other global variable. So, valid operations over structures. Unlike classes in Python and other object-oriented languages, structures have a relatively small number of operations which may be performed on them. And you'll see that this is very C-like. So, number one, you may perform assignment. Assignment over an entire structure is assignment to each of the fields of the structure. So you should be assigning something that indicates those fields, like a bunch of values in the curly brace notation that we've seen a couple of times. Number 2, the address of operator. Obviously, if you want to produce a data structure with references to other nodes of the same data structure, you're going to need some way to extract the address of them. So we have access to the address of the operator. Number 3, 2 in 0 counting. What's it called? 0 indexing. Finding the bit width of data structure with size of. So, the size of a structure is roughly the sum of the sizes of all its fields. Sometimes blank space may be included when you're producing the addressing for small variables. There's also a tendency to have things line up on like the word size of the memory, right? So like, what might happen in this situation here is like, it'll be X, Y, and then some blank space, and then Z, and then A, because that's like word chunks, if it's a 32-bit word, which, Anyway, sometimes that type of calculation goes on, so you don't necessarily get, like, it's kind of like that thing where, like, Booleans are stored as, like, integers, so, like, they take up a lot of space relative to the 1 bit that you need, but, memory is cheap these days, so we don't worry so much about these types of things. So, here's a somewhat larger example. The comments aren't really coming through on the yellow very well. Anyway, so we have a structure card. We have face and suit indicated as strings. We have a card declared, struct card a card. A card dot face is equal to ace. A card dot suit is equal to spades. We can have a pointer to a card pointer. We can give it the address of a card, etc., etc., etc. Incidentally, this should provoke thoughts in your brains like, I wonder if there's a difference between declaring an array of structures and an array of pointers to structures. There's a difference, right? The pointers are just pointers in the array, whereas an array of structures directly looks more like this. It's more of the two-dimensional array type thing. It's like the difference between a 2D array and an array of pointers to other arrays, right? Am I making sense? Are there any questions? Cool. So, this demonstrates a couple of means of access for these. Basically, we're printing out ace of spades, ace of spades, ace of spades by 3 different access methods. So, access method number 1 is just direct referencing of the structure using dot syntax. Means of referencing number 2 is arrow notation. Arrow notation, as it turns out, is a syntactic sugar for pointer dereferencing combined with field access. So, this is a bit cumbersome, right? This is a bit boring. You can just write with an arrow instead, hyphen greater than. Make sense? Yeah, I think I've got a slide on it actually. Yes, so, in the previous example, you may have noticed, because I may have pointed out to you, a pointer to a structure type. When you have a pointer to a structure, you access the fields of the structure pointed to using the arrow. This is syntactic sugar for pointer dereferencing and field access combined into one operator. So, if x is a pointer to a structure and y is the field of a structure, x arrow y is the same as dereference x and extract y. It's almost always more efficient to pass structures by reference rather than by value. So when you see structures later on in the assignment, assignment 2, you will see them being given by reference most of the time. Remember that C passes things by value, right? So if you had one that was slightly larger than this, say 50 elements in your structure, to pass the structure in directly would be to pass essentially 50 input variables into your function, which is a lot. Even though you're kind of technically doing that by putting a reference to such a structure in. It's just, you want to try to minimize the amount of data that's required by a function to just to like initialize the stack frame. So that's why you want to use pointers to get data into these things. If that makes sense. Does that make sense? Question?
So would we not be able to use this arrow here if in a few slides back you hadn't defined like the pointer as the address of the structure?
Correct. So if we return to the previous example, right here, if we tried using arrow notation instead of dot notation here, basically that might result in a segfault, actually. Basically, you're trying to dereference as a pointer something that is not a pointer. I believe this is one of those classes of errors where GCC will warn you that you're doing it, if you've got like all warnings enabled maybe, and just let you do it and get yourself into a segfault that way. Right? It's like the same reason you don't dereference integers. Make sense? Good. So, you can allocate memory to a structure pointer the same way as anything else using malloc or calloc. Don't forget to free. So, very often, you might have, well, we'll kind of get into this when we talk about trees, but you might have a data structure, right? Let's say you had a tree, right? Right? Basic binary tree, right? Basically you would define one of these nodes as having like a left and a right pointer to another node, right? And then some value, right? So in cases where there's no node going off to like in places where the tree structure ends, these guys would point to null, right? In order to create a node on, say, the right branch, you would malloc the size of another tree node. You would take the pointer returned by malloc, and you would assign it to the R right here, right? So that would give you a new node, and you'd initialize it and do whatever you wanted with it. Does that make sense? Cool. So, are there any other questions about structures? Because if not, I'd like to talk to you a bit about Bitwise, because that is kind of a topic that's necessary to cover in a C course, but doesn't really fit anywhere else. You guys ready for some arithmetic?
Sure.
Awesome. Excellent. So, bitwise operators will become very useful to you at some point probably. Even if you do not end up doing anything with embedded systems, they're used quite a lot in embedded systems. But even if you don't use them in embedded systems, these are often the fastest and most efficient operations the CPU can perform. And, you know, you can do things like squeeze power savings out of a program by replacing some operations with bitwise operations. But anyway, and they have applications in like checksums. You'd be surprised at the places these things pop up. But anyway, so bitwise. I'm going to erase this board. So, to say bitwise is to say according to the bits. So, basically, rather than considering operations on whole numbers, the way that we have been, used to performing them so far, we are performing logical operations on the bits constituting the number themselves. So let's say I had two binary numbers, 1, 1, 0, 1, 1, 0, 1, 1, and 1, 0, 0, 1, 0, 0, 0, 1. I think that will give us that 1, 1. There we go. Okay, so two binary numbers. Bitwise AND, right? It is a logical AND operation performed on the bits themselves, which constitute the number. So that would be 1, 0, 0, 1, 1, 0, 0, 1, right? Question? No? Okay. So that's bitwise AND. Bitwise OR it's the equivalent operation but with the OR operator instead of the AND operator. So anytime a 1 appears, the result will be 1, and the result is 0 only if no 1s appear. So you have a 0 here and 1s everywhere else. In general, I know it looks like a 1, but single ampersand is bitwise AND. Single vertical bar is bitwise OR. I know that this looks like it's the prefix address of operator, but C figures it out. It can tell the difference when it's being used as a prefix operator and when it's being used as a infix binary operator. XOR is exclusive OR. This is one that you probably haven't heard of. XOR returns 1 if the inputs are different and 0 otherwise. So it's like OR if you took anything that would and made it 0, right? So same, different, same, different, same. XOR. Make sense? Good. Left and right shift are very straightforward. Let's just, let me do it in a different color. If you take left shift, or that's right shift by 3, then it just says 0, 0, 0, and then it continues on with these numbers, 1, 1, 0, 1, 1, and then the rest is truncated. Make sense? Same thing with right shift. You or sorry, that's left shift, put the zeros in here, and then you 1, 1, 0, 1, 1, which is, you know, this portion and that portion for the top case of the number, which is being retained, right? In terms of arithmetic on integers, these are actually numerically equivalent to division by 2 to the power of n, where this is n, and this is equivalent to multiplication by 2 to the power of n, where you're shifting by the number of bits, right? Because when you move a number over, you're multiplying it by 2 because it's a base 2 system. It would be the same thing as if, like, by, you know, if you had a decimal number that was like 73 and you made it, you know, 7300, then you've moved it over by 2 and you've also multiplied it by 10 to the 2, right? Because base systems and numbers and all that fun jazz. But yeah, does that make sense? So I think I've got a number of slides that have already done basically the same thing that I just did on the board. Question?
What does complement do?
Oh, sorry, it inverts the bits. So yeah. So if I were to take that top one and do the complement, it would just be 0, 0, 1, 0, 0, 1, 0, 0, because you just flip each bit. So, good. I think I can actually skip all of these because it's basically the exact same thing that I just did on the board. But maybe this makes some sense with respect to left shift operations. But you know, you bring in zeros and everything gets shifted down by 1 with left shift. So we consider left to be towards larger place values in big endian systems, which are most of them. Sometimes you have exotic systems which are not, but you know, I think mobile phones might not be, they might be small endian, but so big endian versus small endian, have you heard about that one? No? Okay. So this might be the last thing we talk about today, and then we'll have to continue this on Monday. So, in the 1700s, a man by the name of Jonathan Swift wrote a book called Gulliver's Travels. In this book, the titular character, Gulliver, travels to a set of islands where the people there are very small, called Lilliputians, and he is a giant by comparison. There are 2 neighboring kingdoms of Lilliputians in the book, which have been at war with each other for 200 years. And the thing that started that war is which end of the egg they crack their eggs at in the morning to make their breakfast. So, if you have an egg, you have big endians who crack it at the big end, and you have little endians who crack it at the little end. Obviously, cracking it at the big end is good and virtuous and just, and we do not associate with those heathens who crack their eggs at the little end, unless, of course, you crack your egg in the middle, which is, you know, probable. But anyway, so essentially, this has to do with the manner in which data is stored inside of a computer. So if you imagine an integer as having, or a, you know, there, that's 8 bits, that's a character. It all depends on which of these bits is the most significant, right? So if you have a number, if you read that backwards, you get one word, you get one number. If you read it forwards, you get a different number. You get a different number, right? It matters to the computer system which one of these you use, right? So, if this is the most significant bit, and this is the least significant bit, then you are a right and proper big endian. However, if this is the least significant bit, and this is the most significant bit, then you are a heathen that deserves nothing but death, because you are a little endian. So that is the actual origin of the nomenclature, because people in the past were more literate than they are today, I suppose. But yeah, so overwhelming majority of the time you're going to be in a little or in a big endian situation. But occasionally strange architectures may put you in a little endian situation, in which case the definitions of left shift and right shift have been reversed with respect to the analogy with division and multiplication by powers of 2. Does that make sense? Question?
So when you left shift or right shift, you keep the same number of bits?
Yes, absolutely. The amount of space in memory which has been dedicated to that number does not change, right? So when you are shifting this way, you are losing data off of the most significant bit side. When you're shifting the other way, you're losing data off of the least significant bit side. In general, it's actually a bigger deal to lose data over here than data over here, because this is more significant. Yes?
Why would I want to do that? Like, what's the purpose of left shift and right shift? Like, what's an example, like, what would I use it for?
I can answer it, but you won't want the answer. Okay, so I'm going to have to pull up notes from a different course, so bear with me for a moment. Let's see here. Here's GTIO. So this is a little endian system, but see right there? So very roughly, this is an application from embedded systems design. This is actually, this is an overview of how general purpose input-output pins on an ARM architecture CPU are meant to function, on a modern one anyway. Essentially, the way that it configures, in this case, output, like you take data from your program, you write it to a particular register, and then the electronics take care of driving a high voltage along a particular output pin, or output signal that can go power an LED or something, right? You have a number of registers in memory stored at particular addresses, right? You must set one bit in this register and leave the rest of them 0. One way of doing that is to take the number 1 in unsigned long arithmetic and then shift it down by the number of places that you want that, depending on the final position you want that bit to arrive at. Then you bitwise OR that with the existing value in this register so that you don't disrupt any 1s or 0s that are hanging out in any other spots, right? So this is that would be an application of bitwise arithmetic. Doesn't come up much for programming on computers, significantly less so. But I would also point out that there are how many mobile phones are there in the world as compared to desktop computers these days? Right, quite a few. And it's this this is the process by which your camera program tells your cell phone's camera to turn its flash on, or to flash its flash, as it were. Or the flashlight program is setting the same bit in the same register to send the same signal to your flash LED to turn on. This is what underlies that process, and it all relies on bitwise arithmetic. Any other questions? Understanding that if you ask a question, you might get a dangerous answer, like that just happened. Yeah? Okay. All right. Well, see you Monday then. Good luck on the lab today.